conductivity. Okay, so if it is electrical conductivity, where will you apply? Probably in mineral exploration, hydrology. Okay, now let's see what it is. What it is electrical? Very, very simple method. You see, you have, this is your ground surface. Okay, so you have one electrode. This is called current electrode, and this is second current electrode. So you send some current from this current electrode, and you have two electrodes, which is called potential electrode, and you measure the potential here. The current causes a potential difference. Naturally, we know that if you send a current within any formation, it will have a potential difference. Now, when it goes to the ground, depending upon the rock type and the fluid property, the potential difference will have different potential values. Okay. Now, using this, what we compute ultimately is a parameter which is called apparent resistivity of the soil and the rock, and they are estimated or calculated based on as a function of depth or of position, a function of depth or position. Now on your right you see a profile. Okay, this is the instrumentation part of it, where you send the current here, and at the same time you measure. These are the batteries here. You can see that. This is a very simple method, but very, very effective method. Okay. Now, there is another very simple method of electrical method, which is called self-potential method. What is that? It also measures the potential difference. It also gives you the physical properties of electrical conductivity. Now, how it works? What does it mean by self-potential? You don't send any current here. So what happens? When groundwater percolates down through the metallic sulfide minerals, it acts as a natural battery. And when this current flows through the ore body and back to the surrounding groundwater, it acts as an electrolyte. Okay, so you see here the chemistry is coming, isn't it? Chemistry. Then the Mother Earth is working as a chemistry. The groundwater percolating through the sulfide, generating a kind of natural battery, which sends a current, and you just measure the potential difference. Wonderful tool. And these are some of the things, being used extensively for years in mineral exploration, in hydrology. Similarly, this is also another tool which is called induced polarization, which measures again the polarization voltage. Now, what is induced polarization? You must have heard the name of Schlumberger. Those who are in the final year or probably fourth year, there's a big company called Schlumberger. Primarily, they work for oil and gas, multinational service companies. Okay. There was a person called Conrad Schlumberger. He started his career in resistivity measurement. So while he was measuring the resistivity of a rock, he all of a sudden, realized that he's able to also measure the conductivity of the rock. And there he named it as an induced polarization. Okay, this is a wonderful, very simple tool. So in induced polarization of IP method, which is part of the electrical method, you are not only measuring the electrical conductivity, you are measuring electrical conductivity as well as the capacitance. And using the combination of these tools, you are now more confident to talk about your subsurface. Similarly, I'll not go here in detail of electromagnetic methods, because I have a slide separately. It's an interesting slide which probably all of you will be very interested to know. Similarly, on ground penetrating radar, I will discuss in one of the slides. So what these are the different methods of electrical principle, where your ultimately objective is to unravel the mystery of the earth and use that in mineral exploration, in hydrology, in geotechnical environment. And some of them, in fact, in EM methods are very popular in some of those oil and gas, application. Now, when we talk about this ground penetrating radar, this is primarily a geotechnical tool. I have one slide which I'll share later on. Now, what about this radioactive, survey? Now, radioactive survey is, we all know that all rocks and soil, they contain some amount of radioisotopes, isn't it? Almost all gamma rays which are detected near the Earth's surface are the results of natural radioactive decay of what? Three primary elements. Those are potassium, uranium, and thorium. Now, this radiometric or the gamma ray spectrometry method, what it does is estimate the concentration of these radio elements which might be present, say 10 meter, 50 meter, or even 100 meter below the, Earth's surface. In fact, when we were a student, we used to do a very regular field work in Ghatshila. I think, I don't know, DK, whether you had been there, because that was part of our radioactive field work, where we used to measure those radioactive minerals and map them. Okay, so the technique is very simple, where we measure these gamma rays which with the radioactive isotopes of these elements which emit during radioactive decay process. And the interesting thing is that each gamma ray has a characteristics energy, and measurement of this energy allows you specific potassium, uranium, thorium radiation which are to be diagnosed with a particular minerals. Okay, they are connected with that. So what are the kind of equipments we use? This is equipment which is called Geiger-Miller counter. Some of you, I don't know if in the physics lab you've seen that. This is the radioactive survey Geiger-Miller counter. It looks like that. You have to carry this. The one which we used was little bigger one, and of course these days you have a digital one, so you get digital reading. With this hand you hold it more towards this earth, and then switch on the battery, and you get a kind of sound also. That means it's measuring the radiation, and you take the reading. And on your right is a picture of one of those magnetometer, which is called proton precision magnetometer. We use this equipment also in mapping in one of those manganese deposits in Nagpur. When we were a student, so we use this equipment in an area called Chaibasha. This gravity survey we carried out in Chaibasha. This was in this particular magnetic survey, also gravity survey we carried out in Nagpur. So these are all different geophysical instrumentations. Okay, so and next is wildlife logging. What is wildlife logging? I have a very interesting one slide, so I'll discuss it there. So let's try to understand. This is one of the electrical methods. I said, no, it's not possible to cover everything, but I thought that it would be interesting to give a flavor of those different kind of tools and how exciting, and adventurous these tools are. In fact, when I was, in geophysics, I just wanted to be a person running this kind of electromagnetic survey, when I saw that you need to fly with an aircraft and all this kind of survey. So all kind of excitement we had then. So what it does, it measures actually electrical conductivity. Where from it comes? It comes from the rock and the pore fluid properties. Now, what are those conductive and not so conductive stuff? Say graphite, clay, then sulfide minerals, then saline water. They will show greater conductivity. Okay, as compared to the groundwater. Groundwater, typical groundwater, fresh groundwater should be non-conductive. We all know that. This is the kind of experimentation probably we have all done in our school or in 11, 12. Now, what is this? How we carry out this? Very, very interesting. You see that you have a helicopter here. So here you have a helicopter where you have a transmitter and you have a receiver coil here. Okay. So this transmitter, it sends an electromagnetic signal, and this electromagnetic signal induces an eddy current. This eddy current means which is generated by a magnetic field. The current which gets generated with magnetic field, you all know. And then when it hits that buried anomaly, then it's get reflected back or gets scattered and detected by the receiver coil. And then we do some kind of processing. There's certain basic processing. I'm not going into that detail. And then we ultimately measures this map, prepare a conductive map, or we call conductance map. Now, a lot of mineral and oil and gas, especially the gold deposits, I think most of will be very, very interested, because Bihar has probably more than 40%, 44% of the India's gold deposits. And these are the kind of survey I'm sure some of will be doing, if not today, tomorrow. So these are the techniques which are extensively used and was very successful all over the world. And many such examples we'll find in Africa and also in Australia. I've seen some of those work in Australia also. Now let us see a map, okay? This is the map of Australia, and the survey area is here. And this area is called Patterson area. This area is divided into two, Patterson North and Patterson South. And let's see what are those. Here the outcrop, the deposits are primarily the outcrop or at a depth of 500 meters, okay? Now you see the map which has been generated here. What do you see here? You see a kind of a kind of alignment, isn't it? Deposit alignment. Now, what you see here is electrical conductance. Now, I was, to be very honest, I'm not an area expert of this, because I took an example of AEM, because many of you probably interested for gold, mapping. I'm a person from from seismic and some idea about gravity magnetics and all that, because that's a part and parcel of our job. But AEM, I have very little experience, so I was fairly surprised to see. I just forgot that that copper, the conductance of copper is higher than the gold. In fact, out of silver, gold, and copper, silver is max, followed by copper, and then it's gold. So if you see the high conductance value, the Nifty, the copper deposits shows the high conductance, and it follows a kind of lineaments. You can see that. Next, you see the Telfer gold deposits. Telfer gold deposits is this one, so it represents a kind of color. So this is probably the aerial extension of this gold deposit. Now, next is manganese, which is identified by this deep blue color. So this is probably the aerial extension of this manganese deposit. So how beautifully, I mean, there's a link. I have taken this from government of Australia dataset. These are all available. You can go through it. I'll share this slide, don't worry. So you can really have a look at it, and it will be a fantastic picture. Now, what about the seismic? Very quickly, I'll go. What is seismic? You can have an on-land acquisition, you can have a marine acquisition. Now, in online, what do? You use a kind of vibrator track which generates, some kind of vibration, and this vibration generates an artificial earthquake of very small magnitude. And then you lay receivers at regular interval, and these receivers and then connect it to your track, recording track. So the signal goes down below, and as soon as it gets a reflecting surface, an interface, it's reflected back. It's something like a sunlight hitting your mirror, and it gets reflected back. So we record these signals, and then we process and finally process the signals. Similarly, in case of marine, what you have a ship, you have a cable. These receivers called geophone. These are actually the receivers, and here also these are also the similar receivers. But these receivers are, these are all clapped in a cable, and this cable is filled with oil so that it can float. And you have a source signal here, and this you create an artificial earthquake using something which is called air gun. So you bust those air gun, it is a kind of boom, and then it goes, and similar things like it, as once it hits the interface, then it gets reflected back. Part of it, of course, transmitted, part of it will absorb, but this reflection will also depend the quality material of the interface. Okay, so there actually we measure the quality of this interface or the rock type. So this is in fact in the brief of the seismic. This is extensively used in oil and gas exploration. Oil and gas exploration and development cannot be carried out without seismic. And this diagram, what you see is a 2-dimension. That means you will have an image which looks very something like this signal. Now let's see some of those very interesting, probably some of you will be doing this when you join some oil company. This is a lot of fun, full of fun. On your left, the picture, you see this guy. Let's first see the center picture. This guy, the driller, is drilling a short hole. And once this short hole is drilled, then the dynamite will be lowered. And then they will blast, which will create an artificial earthquake. Now see, it has been blasted. So you can see that kind of smoke. Now, if you cannot have a dynamite as a source, then what you do is you carry this. This is called vibrator. You can see the pad. This pad, hits the substrate regularly imprintable, like boom, 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 boom kind of thing. So it will generate a kind of vibration and an artificial earthquake. These are the guys who are laying the cables. We are full of adventures. Sometimes we ourselves have done it. Sometimes you encounter this kind of land. Sometimes you go to the hill. It's very difficult. Sometimes you encounter desert. Sometimes you lay the cables in water bodies. And these are the kind of cables which you lay. Okay, these are the kind of cables. Now, in case of offshore, what happens? This is again, you see, there's a ship which is acquiring the data, and now you can see there are white lines. These are different cables. So what it is doing, it is not only measuring data from one point, it is measuring data from all the different points. So ultimately, when you acquire the data, you are not acquiring one line information, you are acquiring 3-dimensional information. Okay, and how the data will look like? This data will look something like this 3-dimensional data. Okay, this is a 3-dimensional data. I'll just come to that. Now the source, we talked about air gun. What is this air gun? Now the modern air gun will look something like this. Okay, now there are receivers. You see some of the receivers here on the left side of those screen. These are the receivers. One of the receivers could be here, which can float with a streamer. Okay, there could be another kind of receiver, which will go at the sea bottom, which is called CBed Acquisition. We go to the sea bottom, position itself. Now these are so very advanced kind of receiver. You just lower it from your ship. It are all programmed. It will take itself. You don't have to go and place it. These are all programmed. This particular receiver will only stop at a very specific position. And once the acquisition is over, it will send a signal, and it will come at the bottom at the sea sea surface level, sea water level, and then you just retrieve them. So these are very, very advanced techniques. Now, if you look at the seismic data, now you know what is seismic now. Now, if this data is given to you, you see some of those very interesting events, isn't it? You see some of those very bright events. Now, what are those bright events? These bright events are the gas deposits. You see, gas deposits are giving you some of the bright events. Why it is so? Because gas will have lowering of the velocity. What we measure the impedance contrast. What is impedance? Impedance is basically velocity multiplied by your density. Now, it is your your gas will be only entrapped in a formation which is little lighter density wise or soft, so that something like a sponge kind of thing, so that gas can be accumulated, and therefore you will have, I'm not going in detail or explain because this is a little difficult term. So you just remember, if you have a kind of gas deposit in seismic section, it looks something like this. Now, if you look at this, you can very clearly see there's some kind of discontinuity here. Okay, in the slide number on the picture B. So these are an indication of the faults. You can see the break here. This is the basement, then you can see the break, and you can see the fault coming up. It's a very up. It's coming from here, and there's another set of faults here. Now, here on the picture number C, you can see some of the flat spots, and you can see the salt dome. Okay, so these are so very clear here, and similarly you can see some of the bright sand packs and some of the anticlinal closure. This anticlinal closure is not very clear in the slide, but you can really identify some of the patches which are very strongly indicative. In fact, this is this. Okay, so the seismics gives you so much of information. Now here in seismic, what we measure two-way time. That means a signal, what we measure, the time taken for a signal to go here and come back and gets recorded. So we measure two-way time, not depth. This is very interesting thing. Now, how to convert into depth? If you know the velocity of this formation, then you can multiply that velocity with the time to estimate the depth. Okay, this is very simple, but it is not so simple when you do the work, in fact. Now, on your left, what you see is your seismic data, the 3D seismic data. Now, why I said the geophysics is not only physics, it's also mathematics, because this really does not give me all of the information. Suppose you want to extract the rock properties from here, then you have to use some kind of mathematical model. तो हम क्या करते हैं, ये जो seismic data 3D seismic data है, इसके ऊपर हम कुछ एक्सपेरिमेंट करते हैं. एक्सपेरिमेंट करने के बाद कुछ मैथमेटिकल मॉडल बनाते हैं, एंड वो मैथमेटिकल मॉडल के हिसाब से ये जो seismic data है, ये seismic data को हम एक प्रॉपर्टी में कन्वर्ट करते हैं. मान लीजिए ये हमने जो एस्टिमेट किया है, इट इज अ डेंसिटी क्यूब. So probably these patches you can easily make out कि ये जो blue patches है, this probably represent one type of rock, and this represent another kind of rock, and these are kind of low density rock, which is sandwiched between high density rock. If I am trying to explain in a very layman way, okay, so. That's the reason why I'm saying it is just not the physics, it's a mathematics also. So using mathematical model, we convert this two-way time, this property, which is we call a reflectivity series, to a rock property model, okay, which gives you a more confident way to look at the Mother Earth. Now let's go to a geotechnical application. Okay, so we are now engineers. Okay, now we are geoscientists, 100% people who want to map subsurface. We want to map something which is buried at 4 kilometers, 5 kilometers down there. Now we said no, we want to map something which is buried maybe 50 meters, 10 meters, 5 meters from the earth surface. So there comes the application of ground penetrating radar. This application is very simple, like conventional radar. Uses radio waves to measure the structures and anomalies which are buried inside. Now what it has actually three components. The person who is running this, it has a antenna, transmittal antenna, it has a recording antenna, and there's a controller unit which does the computations. Okay, now simple, fundamental is just fundamental. Okay, what you do is your high frequency radio signal is transmitted to the antenna, which travels down. And if there is a buried body, even if it is a a cave or a tank or even a dead body, it can detect. It hits the object and different electrical properties from the surroundings and they get scattered and the object finally received by the receiving antenna, and which when processed, then it will give you some kind of images. I'll show you some of the images. So what it is, in seismic we are measuring what? Travel time of seismic waves. Here we measure the travel time of the electromagnetic impulse. Okay, and these are widely used in geotechnical engineering and application in archaeological survey, and not only that, even in forensic investigation. Okay, so how the data looks like? Something very similar like seismic. Now here it generates some kind of cone as soon as it encounters some kind of abnormalities. Now you see there are underground storage tanks, and it has mapped the underground storage tank. These are the pipelines, different pipelines, laid within the underground surfaces. So if the underground, these are the very pipeline image very well. So if there is a, if the body of the pipeline is little damaged, it will not get such a strong images. So probably from there you can identify कि भाई pipeline की health कैसे है. Okay. Now from here I'll now come to the borehole geophysics. Why the borehole geophysics is very interesting? This is also known as wildline logging. See, I mean, when we do a measurement in seismic, we measure to a time. But ultimately, when you drill a well, you cannot tell the driller कि भाई आप 2.67 second में drill कीजिए. नहीं, you have to tell them that drill at 1560 meter. There is my object. There is my object. So what we do is, this is the well drill. So where we do the borehole geophysics, you need to have a wellbore definitely. So you lower this, this is called zone, okay, where you have a receiver and also a transmitter. So what we have, these logging tools, normally they have a receiver and transmitter which are lower to the wellbore, and what it measures, it measures in situ rock formation. Why it is important? See, the point is, if we go drill a well and take a core, and when you bring the core to your surface, what happens? The core is now not in the in situ condition. Now the temperature has changed. The atmosphere, now it is in atmospheric pressure. So environment has changed. So whatever measurement you do, this measurement will not give you the correct picture of the rock type which is present maybe at 3 kilometers. So this is a tool which is a calibration tool where it is just like, there's nothing like seismic data. If you ask me seismic data, it is called soft data point. If you take a core sample, there's nothing like that, but you cannot take always core. Core is the hard data point. That means you really know what is the density of the core. Okay, you know what are the contents of the core. But in wildline logging, sits just in between these two. This soft data point and the hard data point. So, and it calibrates between these two. Now, how it does it? It has several tools. All measurement techniques are based on what we discussed on resistivity, gamma, density, and all that. So several tools are clubbed together and they are run simultaneously using a logging string. This is called logging string. So these tools are run, simultaneously. Now here, let us take an example. Okay. Let us take a case where you have a formation. This is the shell, extreme left. Okay, this is a shell and you have a sand formation. Now, if you take a gamma, now shell will have what? You will have more of radioactive minerals. So it will have a higher gamma value as compared to sand. So we know we are interested in shell, not in, we are interested in sand, not in shell for oil and gas. So we have to map this sand. So we have mapped this sand using gamma. But the point is, we are not interested for the entire sand. We are interested only in the hydrocarbon zone. So we have to find out where you have the hydrocarbon and where you have water. So what we'll have, we run a resistivity law. Now, if you have a hydrocarbon, you will read high resistivity. So you can see that within the entire sand, this is the portion where you have high resistivity. And this is the portion where you have low resistivity. So we are interested only within this zone. Okay. Now again, then the driller will ask you, okay, this is the hydrocarbon, but which one is gas and which portion is oil? Okay, fine. We have answer to that also. So what you do is, you have neutron porosity. There's one kind of log, and there is another bulk density. This one is the bulk density, and this one is the neutron porosity. Now you see, the neutron porosity reads a high value against gas, okay, and the density reads a low value against gas. So what you get a kind of crossover on the loop. So from here, finally, you can say, out of this entire sand, we have gas this much, say 15 meter. We have oil, say 20 meter, and rest is brine. Now, when you do all these measurements, you are going down the wellbore, and you are taking all the measurements with depth. Okay. And from here, you can always generate, using again the mathematics, we can generate a kind of, seismogram, which is called synthetic seismogram, to match with the seismic. You generate a synthetic seismic from these informations, from these informations. Of course, for there we need a sonic. I'm not going in detail of that. And then you match those recorded seismic with your synthetic seismic to say what is my calibration point. Not only that, from here you can generate some kind of time depth curve to say कि भाई ये जो top है of the sand is ये seismic में कहाँ पे आता है, और ये अगर यहाँ पे आता है, से ये अगर यहाँ पे आता है, तो I know that say this is at 750 millisecond, because it is 750 millisecond, and here in 750 millisecond means my depth is probably at say 7075 meter. Okay, so this time and this is depth. Okay, so similarly again I go back and say, okay, this was my top and this is my bottom. Now this bottom is what? This is a 750 था, यहाँ पे मेरा से 1200 millisecond है. So 1200 millisecond. Okay. So 1200 millisecond maybe I say, okay, my 1200 millisecond probably somewhere here to the gas cap.
Sorry to interrupt you, Partha. We are left with 7 minutes now.
Okay, fine. I'll just quickly go through this. This is an interesting example of gold exploration. So many of you would be interested to know what is the gold exploration methods and how we can make use of it. Now, Bihar, as I said, it has about 223 million tons of gold reserves, and these gold levels are normally high variables in terms of quartz vein, large disseminated deposits, and located in variety of geological deposits. Now, what are those wide range of geophysical signature we have? We should have a magnetic susceptibility and remanence, and so magnetic survey will help me. Then we'll have potassium content, which is showing high potassium content that can be that will give rise to an increase in radioactivity. So we can do a radioactive survey. We can have an electrical survey because that gives me a high electrical resistivity value, which goes up to the 2 order of the magnitude. So ultimately, what I'm trying to say, you can use different methods to ultimately reduce your uncertainty in any geophysical method, whether it's oil and gas or in gold. So it's a very quick one. I'll just, because some of will really find very interesting. So suppose you want to go for a gold exploration. This is not my area of expertise, so probably you have to bear with me. So what do? You go for an airborne magnetic survey where you delineate the major structures. Then you go for a radiometric survey, which ultimately help you to detect the potassium enrichment, and this will ultimately help, finally gives you alterations. Then gravity survey to map the major structures, basement height and alteration zones. Then buried conductivity that we have seen in our electromagnetic survey. Then resistivity of the gold bearing silicified zones, shallow quartz zones, they are commonly detectable by resistivity techniques. So you see, I mean, these are all different methods, and ultimately you are making use of all these techniques to reduce your risk of uncertainty. So these are the combination of different geophysical tools, and these are being used to map different gold deposits, and these are the different areas of Australia, then Solomon Island, New Zealand, USA, Australia, New South Wales of Australia. All these different techniques have been, integrated to map these gold deposits. So these are very interesting tools. So ये मेरा 2 पैसा का advice है. This is almost going to complete. Knowledge of geophysics will help you to become an excellent geologist. मैं ये कभी नहीं बोल रहा हूँ कि जो geology पढ़ रहा है geology छोड़ के geophysics में जाइए. No. What I'm saying is geology is the Lord Rama. Geophysics is your, Lakshman. So the combination of these two is very important. If you want to be a good geologist, you should have some idea of geophysics. If you want to be a good geophysicist, you should have a good idea of geology. This is very important. It is not a rocket science. Understanding of the fundamental of physics, mathematics are good enough. That's good enough to be a good geologist and good geophysicist. This is an excellent opportunities as a geophysicist. You can really, some of you probably after your graduation, or some of you probably after your even MSc, pursue your career as a geophysicist. If you like adventure, geoscience is a subject and not IT, to be very honest. Okay, that's and one more important thing is networking. Networking is important. I mean, some people might ask why networking. This is an area of competition and cutthroat competition. So get connected through your seniors. Talk to the industry's experts. There are a lot of social media avenues available, LinkedIn profile, Facebook. Connect to your professors. Maintain a good relationship with your professors. Okay? You look for some good mentors and be the member of the professional body. There are a lot of opportunities for the students in societies like SEG, SP, AAPG. Be the member. Take part in different competitions. Okay? That will give you better visibility and connectivity. Because, I give you an example. Suppose you're applying for an MS or a PhD abroad, and you and another person scored the same marks, then a letter of recommendation from your professor or from a professional expert will definitely give an edge over your other guys. So be very open, keep your eyes open, and listen and read. Listen and read and keep in touch with the industry. So this is very important. And lastly, believe in yourself and give in a movie called 3 Idiots, they say that all is well. And so you have to always pat yourself saying you are the best. And if you have that kind of, mental makeup, I'm sure that some of will be an excellent geologist, geophysicist, and whatever you do will really be one of the top-notch guys. And as far as the mentorship, I think I request to my good friend Professor Atul Pandey that probably this is the time. You are a very dynamic person, and to students, I request you have a fantastic head of department and faculty. So make use of that, build a kind of network, and have regular sessions with the industry experts, and learn from each other. I learn from you. You also learn from me. That's how it is. And to be very honest, I am willing to take two students, and I am ready to mentor one from geology and one from geophysics from Patna University if anyone is interested. And my preference would be one boy and one girl student. So this is what I really wanted to say. And this is one of my seniors. I just, without her permission, I took the picture. What I'm trying to say to those girls who are present here, the lot of geophysicists, and you see Dr. Nandini Nityananda, I call her Nandini Di. So she graduated with geophysics in 1967 batch. Okay. And she did wonderful work in her career. So if she could do it as a 67 batch, what sky is the limit for you. So that ends my presentation. Thank you so much. I wish you all very success and wish you good luck. Thank you so much. Now over to Professor Pandey.
Thank you, Partha, for excellent, brilliant presentation. You have not only covered the basics of physics, how it could be employed to solve the geological problem, but also the opportunities which are available for the youngsters and students who opt for geology. But yes, rightly said that the students who are attending this program, simply opting for geology won't make their career. They have to go with different aspects of science, as rightly mentioned by Partha, physics, chemistry, mathematics, and all that is required, that in today's competitive world, a person from geology, if you have a good background in physics or IT, then sky is the limit for you guys. So thank you once again from the Department of Geology. The floor is open for discussion. If any student, if you wish to ask any question in Hindi or English, faculty members are also attending this session. So those faculty members, if you wish to interact with Partha, you are most welcome. We'll have 5 to 6 minutes of discussion before we end this presentation of Partha's on Flavours of Geophysics. I can see one Kuntal Chandrachud, you have raised your hand. Kuntal, you have a question?
Yes, sir.
Yes.
My question is, sir, how to become a planetary geologist?
To be very honest, I really don't know much about it. That's not my core area. But what I can tell you, like from what, as I said, that one of those guys who did an internship under me is working with NASA. So you can really, there's a lot of opportunities as well. But you can probably visit their website. Yes, and there are universities, I understand, because he took some special courses in some United States universities, and some of the courses are free. So you can get yourself enrolled and get connected with the people who are working in these areas. But I am not an expert on this field, so I don't like to comment beyond that point.
Okay, thank you, sir. Thank you.
Geochemist are in. There's someone commented.
Department
IT sector to geophysics. Kuntal, this was also your question. Is there any connection with IT sector to geophysics? Yes.
Yes, sir. Yes, sir.
There's a huge kind of connections, because a lot of applications, especially geophysical application, needs coding, programming. And these are based on high level of mathematical modeling.
Yes.
And the person who has knowledge of geology and geophysics, then definitely he would do a much better work while developing those software packages, because he doesn't have to understand the fundamental of how seismic works or how a resistivity survey is carried out. Okay, yes, so it gives you a fundamental and the background work, and definitely it works. And I know many people who are working in IT areas. there are a lot of developers and they are very highly paid jobs actually in IT
Yes, yes.
sector. A lot of people are working in, as I said, ML, machine learning, artificial intelligence, data science. Because again, in areas like oil and gas, mineral, there's a huge data, huge kind of data. So
Yes.
all the data is not important. There's part of the data important. So data mining is very important. What are those data you really need or some sector needs? So mine those specific data from a huge bank of data and not make it a big structure and ultimately not make use of it. So data mining is an area where there's a lot of scope and people are working.
Thank
Yes.
you, sir.
I think a lot of people are interested in astrophysics. Wonderful, but I am not an expert on this. So
Any
I have given my. I'll share this slide pack with you, Atul Bhai.
Yes.
You can share that with the students.
Okay.
And in the last slide, I have my email ID. They can contact me and share their views. And as I said, I'm very open. Like. Know more about someone wants to know more about carbon sequestration through geophysics. This is a wonderful area. This is a wonderful area, coming up area, a lot of work, and there's a recent work which has been initiated by ONGC along with IIT Bombay. So carbon sequestration and geophysics is very much related. How it is, there's a technique which is called 4D seismic, which is my specialization. So what you do is, when you inject carbon dioxide within the formation, you really need to know like how this carbon dioxide has really अंदर कैसे रिजर्वर में पहुंचे हैं, कौन सा जगह में पहुंचे, कौन सा जगह में नहीं पहुंचे. So what you do is you do a kind of 3D seismic before the carbon dioxide injection, and during the injection, at regular interval you carry out those acquisition and processing or carry out the same survey. And studying these two, you can really map कि भाई कितना कार्बन डाइऑक्साइड आपने उसमें इंजेक्ट किया है, कितना जगह अभी भी बचा हुआ है. So this carbon dioxide injection और carbon sequestrations में geophysics का बहुत सारे applications है, and some of the applications you will find in Canada and also mostly in Canada, and some of them are also in US. And soon there'll be one in India, and probably we can take that, Saeed bhai, you can contact me. I can share some of the slides and some of the work of carbon sequestration. And there is one of our senior who is working on that. He's from Hawaii University, working on carbon dioxide sequestrations.
So we'll take one more question before we ask our faculty member to propose a formal vote of thanks. If anyone of you, if you have any query, or you can, if you wish to comment anything. Partha, myself, I wish to develop a small lab or some instrumentation facility in our department. Still, we don't have much. So I will request you to just suggest me what are those smaller or basic instrumentation which we should develop in our department.
Okay. So I first thing that I should have some idea like what would be your budget, to be very honest, because if I recommend some instrumentation which is very expensive, I will not recommend that. So instead of that, maybe within the budget you can go for some 2-3 different instrumentation of different processes that probably help. Okay. So if you give me a kind of budget, then I'll have a word with some of my colleagues who are working in this area